All right, I'm going to use a blue to write the solutions here. All right, so let's evaluate the function at 1, 0 first. Okay, so that's going to be 1 cubed minus 1 times e to the 2 times 0, right? That's 1 minus 1, so that's 0. Okay, so this level curve, so the level curve I'm about to draw is going to be f is equal to 0. Find all the point where f is, find all the points where f is equal to 0. How do you do that? Well, I know this is number 3. I'm just doing number 3. I know numbers 1 and 2 will be easy to calculate, but let's go to number 3 first because I actually want to draw a picture here, right here, okay, in this space of the level curve, so I can illustrate certain things. Okay. All right. So this is x cubed minus x e to the 2y, right? And you want to set this equal to 0 because the level curve through this point is the level curve corresponding to the value of 0. Now, of course, you can factor out x. And so this means, oh yeah, do you know how to calculate this, how to solve this? You have something times something is equal to 0. And in the real number system, the only way you can get the product of two numbers to be equal to 0 is if one of them is 0. So x has to be 0, or x squared must be equal to e to the 2y, which happens to be e to the y squared. Remember, e to the 2y is e to the y squared. That's the same thing. So what is that? This means x is equal to plus or minus e to the y. Right? Or you can say e to the y is plus or minus x. Maybe I should say e to the y is plus or minus x. Okay. What is that? Log of x, natural log of x. You take the log of both sides, and that's going to be plus or minus x. That's the absolute value of x. Right? So maybe I should draw a picture here. Okay. Let me draw this picture. And what I'm going to do is, what I'm about to do is to graph this level curve where f is equal to 0. Okay, so what are the points where f of x is equal to 0? Oh, is this maybe, that's not the correct answer here, is it? All right, so I didn't write this correctly. If I take the log of both sides, okay, this is basically saying this is the absolute value of x. And so y is the absolute natural log of the absolute value of x. That's what I mean by that, okay? Yeah. Sorry about that. And so, well, natural log of x, that kind of goes like this. And because it's the absolute value, you know, because you take the square of both sides. I mean, this is what happens here. It is symmetric on both sides. I know it's a hard question here. And maybe you need to go back and study your pre-calculus again. But this is the picture. And then the 0.10 is, of course, right here. So technically, the level curve going through 1, 0 is only the right-hand side, this one, okay, this component. Okay, that's the level curve going through 1, 0. Although the level curve where f is equal to 0 does have the other component. So you have a two-component, you know, non-connected graph, and that is the level curve corresponding to f is equal to 0. But let's focus on this point here, right? Number 1, the question, part 1 says, what is find the direction of the maximum rate of increase? All you have to do is to find the gradient, okay? So if you take this, and by the way, maybe the way I should have done this is find fx and fy. Let's go ahead and do this, right? And you can also do it this way. I would sort of encourage you to do it this way, unless the function is really simple. Find the partial with respect to x. That's 3x squared minus e to the 2y, right? And then with respect to y, well, this one goes away, but you have minus 2x e to the 2y. Do you get that? 2 goes to the front, x stays as x because that's just like a fixed coefficient. And e to the 2y just becomes 2 times e to the 2y. You evaluate this at 1, 0, and this will give you 3 minus 1. Remember, e to the 0th is 1, so this is 2. And this will be negative 2 times 1 times 1, so that's negative 2. All right, so the gradient of f at 1, 0 happens to be negative 2, 2, negative 2. Now, let's go ahead and graph this, okay? This turns out to be 2, negative 2. So that's this. That's the vector. Okay, notice here, it is perpendicular to this graph, and it should be, okay? Because, I mean, that's what it is. And by the way, the line tangent is going to look, let's use a more precise thing here. This is the tangent, okay? This is the tangent line to the point 1, 0, tangent to the level curve, okay? And so, and you can see that, and by the way, if you take the derivative of this thing, okay, if you take the derivative of that at 1, 0, you know the natural log of x has the derivative 1 over x. When x is equal to 1, then of course y prime is 1. So the slope of this line, is, sorry about that, I'm not in the right mode here. The slope of this tangent line is of course 1, because it's 1 over x, where x is equal to 1. Right? And you notice here, this has the slope of negative 1, right? So this is perpendicular as we expected it. So the answer to number 1 is that f, let's say the gradient or the rate of change, the directional derivative is maximized in the direction of, now you could say in the direction of negative 2, negative 2, or you can say 1, negative 1, or typically they sort of normalize this. And so if you normalize this, you know, this is what you get, right? I didn't give you the detail of this, but the length of this, oh yeah, so the gradient has the magnitude of square root of 2 square plus 2 square, which is the square root of 8. That's 2 square root of 2. So if you divide this component and this component by 2 square root of 2, of course, you get this normalized vector. And typically, when you are answering the question about the direction, then you give a unit vector in that direction. That's the only reason. If you say it's in the direction of 2, negative 2, I will not penalize you for that. But typically, you just use the unit vector in that direction. So what I just calculated here, this is the maximum rate of change at the point 1, 0. Okay. In other words, if you are, so let me go ahead and do this again. If you're standing right here, 1, 0, and of course the z value is 0, then you go in this direction if you want to go in the direction of the maximum rate of change. And if you go in that direction, the maximum rate of change will be 2 square root of 2, or the square root of 8. Okay, so that's the part 2. That's part 2 of the question. Now, part 3, I did this already. Draw the level curve through 1, 0, and the gradient of f. I did draw the gradient of f, which is that orange arrow, now the red arrow. And notice here that the gradient is perpendicular to the level curve, right? All right, and then number 4, I'm doing number 4. Number 3 is done, okay, right here, okay. Number 4, I'm doing number 4 because there are a couple of questions in your homework set where they ask you to do this. Find the vector tangent to the level curve, right? So this gradient is perpendicular. Let me draw a picture of this. Okay. What we have is this. You have this and this. This is the gradient, which is 2, negative 2. Okay. So you're going, you know, bottom to the right. This is the direction in which you'll get the positive rate of change. In particular, the rate of change in that direction will be 2 square root of 2. But if you're interested in the a vector that's tangent to the level curve, this is the vector that I want. Okay. So what is this vector? Well, if you want to go in tangent direction, you want this to, that v to be perpendicular to this, right? So this should be perpendicular to the gradient of f, which is 2, -2. Or, of course, it's 1, -1, right? 1, -1 has the same direction as the gradient, which is 2, -2. So do you know how to write a vector perpendicular to it? Yeah, all you have to do is to make sure that dot product is equal to 0. And so you can just write 1, 1 in this case, right? Because, I mean, what do you normally do? You say, see, the thing is, in terms of, in language easily understood by an Algebra 1 student, the gradient has the radius of, not the radius, slope of -1, okay? And so the negative reciprocal of that is 1. And so you want v to have the slope 1. That's another way of saying you want 1, 1. Okay. Now you could also write -1, -1. That is also perpendicular to the gradient. And -1, -1 is also a vector tangent to the level curve. So that would be okay too. In homework, typically they will say out of these two vectors, 1, 1 and -1, -1, pick the one that has the positive x coordinate. And so then you will be doing this. But again, it is standard practice to normalize a direction vector. So you probably should do u is equal to 1 over square root of 2, 1 over square root of 2. So now it's normalized and it's showing you the direction, which is tangent to the unit vector. Okay, so hopefully this wasn't too confusing, right? The last section of this, last subsection of section 4.6 deals with adding an extra dimension. What about w? That is a function of x, y, z, right? And this is easy because it's exactly the same, okay? The gradient is going to be the gradient of f, which is fx, fy, fz, evaluated at the point x naught, y naught, z naught. All right, now you notice here, I can't graph the functions of 3 independent variables, right? Right, but what I can do is to graph its level surfaces, all right? So maybe a level surface would be something like this, okay? Let's say this is where f is equal to 0. Okay, so this is a level surface, and it is the level surface, not a curve anymore. This is the level surface where the value of the function f is equal to 0. In other words, the set of all points where f of x, y, z is equal to 0 would create a surface. And so this is the level surface corresponding to the value of 0. And if this is the point x naught, y naught, z naught, guess what? The gradient, so this is the gradient of f, which is a gradient of w, same thing. This is also going to be perpendicular to the level surface. Okay, so this will be perpendicular to the level surface going through x naught, y naught, z naught. And it points to the direction of the maximum rate of change. Okay, and the gradient has the magnitude, which is the maximum rate of change if you are to go in that direction. So it's all the same, except you just have one extra dimension. But the gradient is still, perpendicular to the level surface. Okay, I want to give you an example, and then I will make one last comment, and then we will finish for this section. All right, consider or think about this function here, f of x, y, z is equal to x squared plus 4y squared plus 9z squared. Okay, so the level surface, f is equal to 36. You know what that is? Set this is equal to 36. Okay, and you can see that if you cross out x, you're going to see an ellipse. If you cross out y, you'll see another ellipse. You'll see if z is equal to 0, you see another ellipse, right? So you will see that this will give you an ellipsoid. Let me quickly draw this. Okay, so if you do careful analysis here, you'll see that this is 6, because I mean 6 squared is 36. So 600 is on this level surface. And what's this point here? For y, that's 3. Okay, because 030 is on the surface. You can see that this will be 36 then. And then the top point here is 1. If z is equal to 1, and so the point 001, for instance, is not in here. This is supposed to be 2, isn't it? Okay, yeah, 2, because 9 times 2 square is 36, right? So yeah, so this is a sort of a football. That is the level surface, not the function, not the graph of the function, which is impossible to graph, but it's a level surface where f is equal to 36, right? Now, if you were to find the gradient, okay, what is the gradient here? It's 2x, 8y, 18z, okay? So for instance, this evaluated at, let's say 600, that's a point on this surface, is going to be 12, 0, 0. And so I'm going to shrink this, but the graph will look like this. That's the gradient, okay, at 600. And next, let's go to evaluate this at, let's say the point 002, okay? This will be 0, 0, 18 times 2 is 36. So this will be something like this, okay? That's the gradient. And so this is the gradient at 600, and I mean the length is 12, and this is the gradient evaluated at 002, and this is a long gradient, long vector of length 36. And that means if you go in this direction, okay, if you're standing right at this point 002, okay, then the upward vertical direction is the direction of maximum rate of change, and the maximum rate of change at that point 002 would be 36, because that is the length of this vector. All right, so that's how you would interpret this. I hope you have an appreciation, although this is sort of a newly acquired appreciation, but appreciation for this thing called the gradient, right? And I'm telling you, the more time you spend with the gradient, the more you appreciate it, just like, a nice person. The more time you spend, the more you understand, and that becomes a part of you. And that's what's exciting. All right, so the one last comment I was going to tell you is this. So if, if you have a w, which is a function of x, y, z, has a level surface, and the level surface is going to be something like this, okay? And it's a, it's maybe a closed surface, maybe it's not, okay? But anyway, if you have this, then the gradient will always be perpendicular. Now, if the inside of this sort of the thing that looks like a balloon, if the inside has a higher value, the larger value of f of x, y, z, then everything will be pointing inward. But I'm assuming here that the outside, as you move away from the origin, the value gets higher, okay? Then this will be always perpendicular like this, okay? And think about this. This is a way to find the tangent plane, right? If you want to find the tangent plane at this point, you need to find a normal vector which is perpendicular to that tangent plane. How do you find it? Well, that's going to be your gradient, right? So this is going to be a very powerful tool as you move forward and in analyzing this, okay? So this is what it looks like, okay? Now, let's go back to, and this is only going to take a minute or two. Let's go back to the function z is equal to f of x, y, okay? You could actually write this as, all right, so you can write this as f of x, y minus z, okay? So the graph of this the graph, which is, you know, like a surface here, like this. The graph of f of xy is all right, so I changed things a little bit, but back to a function of two variables, right? And when you talk about a graph like this, you know, z is equal to f of xy, you have two independent variables, but you can think of this surface as a level surface. What do I mean by that? Well, look, the graph of this is exactly the set of all points where this is true, and that is the level surface of f, capital F now, okay, of f of xy minus z is equal to 0. Now this makes sense because I'm collecting all the points where z is equal to f of xy, but if you decide, or if you define capital F to be this function of three variables, then this entire surface can be considered, listen carefully, this entire graph of the function of xy can be considered the level surface of the capital F corresponding to the value 0, because obviously this is true whenever this is true, right? All right, so as such, okay, you can find the gradient of the capital F. That will be fx, fy, and what's the last component? It's -1. Okay, now you saw this before. This is exactly what you saw in in the approximation, linear approximation, or linearization, or the tangent plane. Remember the tangent plane had the normal vector, which is fx, fy, and then the last one was -1. Also, this is another way of looking at this. Just like, you know, all the gradient was perpendicular, this will give you a perpendicular vector at every single point. Okay, and the equation of these perpendicular vectors is fx, fy, and then -1. Oh, -1 means it's going in the other direction. Okay, so if you go above or on top of it, it'll be negative fx, negative fy, +1. But anyway, that's, you know, all of these are perpendicular to the graph or the surface. So this explains where that -1 came from. I did explain it in another way when we talked about linear approximation, but that's yet another way to find that -1 is the last component of a normal, you know, a vector to a tangent plane. Okay, so much for that. I think this is being good, and I hope you have understood the importance and the elegance of this thing called the gradient. All right, so, you know, you may think I'm silly talking about the elegance and the beauty of gradient, but think about this, you know, that appreciation of how nice things are, that's really a part of mathematics. You become passionate about the things that you are learning that the rest of the country or the rest of the world, you probably, they don't figure this out because not too many people take calculus 3, right? And so they may not understand what you find elegant or beautiful, but you are seeing the glimpse of this elegant and beautiful world called mathematics that other people may not be able to see. Okay, so appreciate as much as you can, and that will make math fun to learn. Not that it just needs extra excitement, okay, because it's already there. But that's how you you get to appreciate mathematics, and if you once you appreciate it, it'll be much easier to learn it because it's fun to understand these things. Okay, so with that, I will see you. Next time we'll do section 4.7. Take care.